Okay, what if I told you that a tiny speck of dust, and I mean really tiny, and older than our own sun, holds a secret that could completely change technology right here on Earth? I know, it sounds like something out of a sci-fi movie, right? But this is a real discovery, and it all starts inside a pretty famous rock that fell from space.
So this is the Murchison meteorite. It's basically a time capsule from space that landed in Australia way back in 1969. And when scientists cracked it open, they found something absolutely incredible deep inside. Tiny, tiny grains of what they call pre-solar carbon. And get this, it's literal stardust. Stuff that was forged in the atmosphere of a star that lived and died long before our solar system was even a thing.
But here's the thing. This ancient dust wasn't just cool because it was old. No, when scientists finally got it under a microscope, they saw that its structure, well, it just didn't make sense. It was put together in a way that seemed to defy the basic laws of chemistry. It was a genuine puzzle. So, you gotta ask, what secret was this thing hiding?
All right, Section 1, Stardust on Earth. To really get what's going on here, we first need to get to know our main character. These weird little things called pre-solar graphite onions.
Okay, so here are the basics. We're talking about tiny, micron-sized spheres of carbon. And we know, because of their unique chemical fingerprint, that they came from the atmospheres of ancient red giant stars. Think about that for a second. That makes them older than our entire 4.5 billion-year-old solar system. And that nickname, pre-solar graphite onions, well, it's pretty spot on. They literally have a core surrounded by layers of graphite, just like a tiny onion you'd find in the kitchen.
Right. Section 2, a carbon conundrum. So we've got these little cosmic onions, but when scientists zoomed way, way in on their core, they found a total head-scratcher. I'm talking about a structure that, based on everything we know about chemistry, just shouldn't be there.
Okay, before we dive into the problem, let's do a quick refresher on the key material here, graphene. Just think of it as a perfect one-atom-thick sheet of carbon atoms, all arranged like chicken wire or a honeycomb. It's ridiculously strong, and it's the basic building block of graphite. You know, the stuff in your pencil.
So, on the left, you've got your typical graphite. The graphene sheets are stacked up perfectly neat, kind of like a brand new deck of cards. But then, on the right, that's what they found inside the Stardust core. And it is a complete mess. It's this tangled, jumbled, unlayered web of graphene that just refuses to stack up nicely.
The researchers who figured this out, Silva and her team, actually wrote in their paper that they saw, and I'm quoting here, an abundance of single straight-line segments, often with a bend in the center. So just picture that. Instead of nice flat layers, they're just seeing all these bent, almost broken-looking lines.
And that became the central puzzle they had to solve. You see, graphene sheets naturally want to be flat. So what in the universe could possibly force them to bend and fold and then get stuck in this totally chaotic mess?
Let's move to Section 3, the Pentagon's power. The clue, it turns out, was hiding in plain sight, right in the basic geometry of the carbon atoms themselves. The researchers found the answer in the power of the Pentagon.
Okay, this is it. This is the big aha moment. On the left, you see normal graphene. It's made of six-sided rings, hexagons. That's why it can tile together perfectly and stay flat. But what if you throw a five-sided ring, a pentagon, into that perfect pattern? Well, look at the right. It acts like a defect, a wrench in the works. The sheet literally can't lie flat anymore. That one single pentagon forces the whole thing to bend and start curling up into a cone.
So, okay, pentagons make cones, that makes sense. But why would they even form in the first place? This is where it gets really wild. The team ran these super sophisticated computer simulations using a program called VASP to see what happens when liquid carbon cools down in the weird, low-pressure atmosphere of a star. And would you look at that? The simulation showed that five-sided pentagons were actually more likely to form than the normal six-sided hexagons. Isn't that crazy?
So let's put it all together. If these pentagons are forming first and more easily, they basically become the seeds for everything else. Just imagine it. In this cooling droplet of carbon, all these little cones start popping up everywhere. As they get bigger, they're bound to bump into each other, get tangled, and then freeze that way. And that creates the exact messy, jumbled structure they saw in the meteorite. They gave it a cool name, too. Pent-first nucleation.
All right, Section 4, from space to lab. Now, that is a fantastic theory, but
You know how it goes in science. You gotta prove it. So, to really lock this down, the researchers put together 3 different lines of evidence: stuff from deep space, stuff they made in their own lab, and data from their computer models.
And it was a really clever 3-pronged attack. First, you've got the cosmic evidence. That's the actual pre-solar graphite they pulled out of the Murchison meteorite. Second, they hit the lab. They actually built their own carbon spheres in something they called an evaporating carbon oven to try and copy the conditions inside a star. And third, of course, was the digital evidence from all those powerful computer simulations we just talked about.
And here's the proof in the pudding, where the numbers just click into place. The team figured out how many seeds would be needed to make the structures they were seeing. If they assumed it was the normal 6-sided hexagons, they'd need about 2.3% of all the seeds available. But if they assumed it was the 5-sided pentagons, they'd only need a tiny fraction of what was available, just 0.24%. And since their simulations already told them that pentagons were super common, the whole theory just fit perfectly.
So, this Pent-first theory wasn't just some wild guess. It was the only model that actually lined up with the math and explained the data from both the ancient stardust and the stuff they made in the lab. Boom! Cosmic mystery solved.
All right, final section. A new supermaterial? Look, solving a cosmic puzzle that's billions of years old is awesome. No doubt about it. But why should you and I care about some messy stardust? Why does this matter to us, right here on Earth? Well, the answer just might be the most exciting part of this whole story. First off, you have to appreciate just how unique the conditions were out there in space. The researchers figured that those carbon droplets in the star's atmosphere cooled down at least, wait for it, 10 million times slower than anything we can do in the lab. That incredibly slow, patient cooling process is what allowed these much bigger, more complex graphene structures to form. So what's the big deal about this messy, tangled-up structure? What can it actually do? Well, think about it this way. Imagine trying to walk through a forest where all the trees are in neat rows. Pretty easy, right? Now imagine trying to get through a dense, overgrown jungle with no paths. Much, much harder. It's the exact same idea here. This messy structure creates what scientists call an unprecedented diffusion barrier. Basically, when other atoms or molecules try to pass through, there are no easy paths. They just get blocked, stopped in their tracks.
And this is the big takeaway, the real game changer. What looked like a chaotic mistake, a flaw out in space, could actually be an amazing technological feature down here on Earth. If we can learn how to make this structure on purpose, we could potentially build all kinds of new supermaterials that are almost impossible to get through. Think about it. Advanced batteries, super tough protective coatings, maybe even better ways to store hydrogen fuel.
So it really all comes full circle, doesn't it? A tiny piece of stardust, born in a dying star billions of years ago, just taught us a brand new fundamental secret about how to put carbon together. And that leaves us with one last really fascinating question. Could this secret from the stars, this recipe for cosmic chaos, actually be the key to building a better, stronger future for us right here on Earth?